Align-anything, training all modality models to follow instructions with language feedback by Jiaming Ji, Jia Yi Zhao, Hantao Lu, Bo Yuan Chen, Donghai Hong, Zhu Yao Wang, Wenqi Chen, Kaylee Wang, Rui Pan, Jihao Li, Mohan Wang, Joseph Dai, Tian Yi Qi, Hua Zhu, Dong Li, Weiping Chen, Zhen Song, Bo Zhang, and Yaodong Yang. The Institute for AI, Peking University. Beijing Academy of Artificial Intelligence, BAAI. Hawaii's Noah's Ark Lab, Beichuan Incorporated, and Taobao and Tmall Group of Alibaba. Abstract. Reinforcement learning from human feedback, RLHF, has proven effective enhancing the instruction following capabilities of large language models. However, it remains underexplored in the cross-modality domain. As the number of modalities increases, aligning all modality models with human intentions, such as instruction following, becomes a pressing challenge. In this work, we make the first attempt to fine-tune all modality models, for example, input and output with any modality, also named any-to-any models, using human preference data across all modalities, including text, image, audio, and video, ensuring its behavior aligns with human intentions. This endeavor presents several challenges. First, there is no large-scale all-modality human preference data in existing open-source resources, as most datasets are limited to specific modalities, predominantly text and image. Secondly, the effectiveness of binary preferences in RLHF for post-training alignment in complex all-modality scenarios remains an unexplored area. Finally, there is a lack of systematic framework to evaluate the capabilities of all modality models, particularly regarding modality selection and synergy. To address these challenges, we propose the Align-anything framework, which includes meticulously annotated 200,000 all-modality human preference data. Then we introduce an alignment method that learns from unified language feedback, effectively capturing complex modality-specific human preferences and enhancing the model's instruction-following capabilities. Furthermore, to assess performance improvements in all modality models after post-training alignment, we construct a challenging all-modality capability evaluation framework, eval-anything. All data, models, and code framework have been open sourced for the community. For more details, please refer to the link. Introduction. Our world is inherently multimodal. Humans perceive the world through various sensory organs, acquiring information in multiple modalities such as text, images, audio, video, and others. These different forms of information often complement and interact with each other. Each sensory channel has unique advantages in conveying specific concepts and enhancing our understanding of the world. With the success of large language models, LLMs, researchers aim to extend these models to handle multiple modalities, enabling them to perceive and generate any modality. This would allow the models to respond using the most appropriate modality, achieving truly human-like AI. Consequently, the research community has actively developed foundational models capable of handling arbitrary modalities. Based on LLMs, people use individual image text encoders or domain-specific decoders for input or output processing, leveraging the MOE architecture and diffusion techniques. In this line of work, each modality is encoded by a single encoder, with non-text modality information being mapped to the text space via projection layers. Additionally, Chameleon has experimented with encoding images during the pre-training phase using fully token-based representations to handle both image and text modalities. However, handling more modalities remains a significant challenge. On the other hand, reinforcement learning from human feedback, RLHF, plays a significant role in aligning models with human intentions. GPT-4 has effectively boosted the model's instruction following using RLHF. Llama series models have significantly improved the performance in code, mathematics, and reasoning through the post-training method, for example, DPO. However, this line of work is limited to single modality. Researchers try to apply RLHF or DPO directly to multimodal scenarios, such as models with text and image modalities. However, these methods, which rely on aligning responses with binary human preferences, for example, one answer is better than another, struggle to be effective with more complex and diverse modalities. ImageBind propose using single modality information as a binding, such as using images as the bridging feature to learn joint embeddings. So, how can we establish a unified preference modeling to ensure effectiveness across any modalities? All modality models refer to models capable of accepting input and generating output in any modality, essentially functioning as any-to-any models. Language can serve not only as a binding across different modalities, but also as a natural human preference carrier. In this work, we propose utilizing language feedback to unify human feedback across all modalities, marking the first attempt to extend RLHF DPO to arbitrary modality space and promoting the development of a general all-modality model. Overall, our work makes the following contributions. Data. The first all-modality human preference dataset, eval-anything 200K, on text, image, audio, and video modalities. Utilizing a two-stage human annotation process, this dataset accurately captures genuine human preferences, aiming to improve the alignment of all modality models with human intentions. Algorithm. The first algorithm applicable to enhance RLHF DPO across all modalities. Learning from language feedback, LLF. Our empirical results demonstrate that LLF enhance RLHF performance across 5 modalities, 5 open source models, and 7 popular benchmarks, which achieves an average 5.83 times improvement than the baseline RLHF. Evaluation. To our knowledge, there is no system specifically designed for all modality model evaluation. To address this gap, we propose the first evaluation tool, eval-anything, tailored for all modality evaluation. This tool not only meticulously constructs evaluation tasks across various modalities, but also emphasizes assessing the unique features of all modality models, such as modality selection and synergy. Framework and open source. To further the alignment of the all-modality model with human intentions, we have released all of our resources to the public. Datasets. A primary challenge lies in the fact that existing preference datasets are predominantly focused on single modal tasks, lacking comprehensive datasets that encompass all modalities, thus limiting further research progress. In response, we open sourced the first all-modality human preference dataset, eval-anything 200K, to enhance the instruction following capabilities of all modality models across tasks such as question answering, complex reasoning, etc. During the annotation process, we observed that introducing additional modal information significantly reduced binary human preference consistency. Therefore, in addition to annotating fine-grained binary preferences, we introduced language feedback as an additional constraint to more accurately capture human preferences. In short, our dataset includes the following. All-modality human preference dataset. We annotate human preference data across various modalities, including text, image, video, and audio, with a focus on instruction following capabilities. One more thing, language feedback. In addition to the widely used binary preferences, we incorporate language feedback, critique, and refinement to improve human preference consistency across all modalities. All-Modality Human Preference Dataset. The eval-anything 200K align aims to capture human preferences across 8 subtasks of all modalities, as shown in Figure 2. With the increase in modalities, the complexity and consistency of human intent preferences rise significantly, driven by the unique semantic characteristics of each modality. To achieve consistent all-modality preference modeling, we decouple annotation targets into 2 types, which serve as evaluation metrics for instruction following. Modality agnostic refers to dimensions that are applied universally across modalities, including prompt adherence, which requires responses to be consistent with the input prompts, accurately reflecting the specified elements; rule conformity, where responses adhere to logical, physical, or scientific principles related to the scenario or theme described in the prompt; information richness, which emphasizes that responses should be thorough and detailed in addressing the query. Modality specific represents preference dimensions tailored to the characteristics of each modality. For example, in video-related subtasks, we introduce 3 additional dimensions: temporal consistency, content coherence, and motion naturalness to better evaluate the details in the output regarding the duration, dynamics, etc. By decomposing the instruction following dimensions, we establish the evaluation standards for all modality preference annotation. More details about the annotation document can be found in appendix datasets. One more thing, language feedback. During the annotation process, there exists a decline in human preference consistency when directly conducting binary preference annotations. As illustrated in Table 1, the introduction of different modalities makes it challenging for binary preferences to fully capture human preference. To address this issue, we introduce language feedback, utilizing natural language to describe discrepancies between the model's response and the standard criteria, thereby improving the consistency of human annotation. Specifically, we provide language feedback for each response, which includes 2 parts: critique, which assesses the strengths and weaknesses of the response based on detailed criteria; and refinement, which offers specific improvement suggestions to enhance the model's instruction following capabilities. Through the quality control process with annotators and training verification, we identify 2 key advantages of using language feedback. 1. As a natural carrier of human preferences, it clearly identifies fine-grained defects and areas for improvement in the responses, providing clearer guidance compared to binary preferences. 2. As a connecting binding, it bridges human intent across different modalities and creates a unified modality-agnostic preference modeling approach, capable of handling more modalities than typical methods. Further examples can be referred to in appendix datasets. Dataset construction. We collect initial prompts from 24 multimodal datasets and refine them based on modality-agnostic and modality-specific dimensions. With existing multimodal models, for example, GPT-4o, we emphasized dynamic temporal aspects for video or quality characteristics for audio to better adapt to each modality. Finally, we gathered the responses from 27 models for the 8 subtasks. More details can be referred to in appendix datasets. Annotation process, inspired by PKU SAFE RLHF, we utilize a human-AI joint annotation process to conduct preference annotations across fine-grained dimensions for each subtask. As shown in Figure 3, for each fine-grained dimension's binary preferences, we assign scores from 0 to 3, following strict guidelines and detailed rationales. Additionally, we collect language feedback from human annotators and API-based models. The annotators provide language feedback for each response by defining the critique scope, performing the critique, offering refinement suggestions, and organizing the critique and refinements into comprehensive language feedback. As shown in Figure 3, Language feedback provides more fine-grained improvement directions for cross-modal responses, serving as a carrier for expressing natural human preferences across modalities. Human and AI agreement analysis, we integrate API-based multimodal models, for example, GPT-4o and others, into human evaluation for binary preferences annotations. To analyze the consistency of the dataset with human preferences, we sample 100 data pairs from each subtask, with 10 annotators to pairwise comparisons, and statistically measure the preference consistency, as shown in Table 1. The results demonstrate that with the traditional binary preferences annotation pipeline, agreement consistency tends to decline as multimodal information is incorporated. This suggests that the conventional pipeline struggles to scale effectively across all modalities. As language-based feedback offers targeted and fine-grained human preference information, higher consistency is achieved across all modalities. Learning from language feedback. In this section, we introduce learning from language feedback, LLF. It utilizes language feedback to optimize responses, synthesizing preference data, which can enhance the performance of all modality alignment. Firstly, we review the RLHF pipeline, including PPO and DPO, highlighting the limitations of binary preferences feedback. Then we demonstrate how to practically implement LLF, including two main stages: feedback modeling and self-improving. Finally, we empirically verify that LLF achieves an average 5.83 times improvement across 5 modalities, 5 open source models, and 7 popular benchmarks. Background and preliminary. PPO consists of 2 main stages, including Step 1, preference modeling, and Step 2, policy optimization. The former involves the collection of comparison data, essential for training the reward model, R sub Rm of dot given dot. The process starts with response pairs y sub 1, y sub 2, generated by the initial model from shared prompts X. Human annotators are then tasked with selecting the preferred responses from each pair, denoted as y sub w is preferred over y sub l given x, where y sub w and y sub l denote the preferred and dispreferred answer. The latter, step 2, is guided by the r sub rm of dot given dot. This process is commonly modeled as a bandit setting, where a reward is obtained from the r sub rm at the end of each response. The RL objective is theta sub RL is equal to the argument that maximizes over theta of the expected value with respect to x sampled from p sub x and y sampled from pi sub theta given x of the reward model function r sub rm of y given x. DPO directly fine-tunes the model aligning with preference pairs y sub w is preferred over y sub l given x. It consolidates the 2 stages of preference modeling and policy optimization in RLHF into one stage. Let theta naught denote the initial model parameters. The optimization objective can be rewritten as theta sub RL is equal to the argument that maximizes over theta of the logarithm of sigma, applied to beta times the logarithm of the ratio of the policy pi sub theta of y sub w given x to the baseline policy pi sub theta 0 of y sub w given x, minus beta times the logarithm of the ratio of the policy pi sub theta of y given L given x to the baseline policy pi sub theta 0 of y sub L given x. Since both PPO and DPO are modality agnostic, intuitively all modality alignment can be achieved with preference pairs y sub w is preferred over y sub l given x, and recent works have also validated its effectiveness. However, the preference of coupled responses are trade-off by different dimensions, for example, their style and correctness. As the number of modalities increases, these dimensions become more complex, making it harder to figure out misaligned behavior with binary preferences. Practical implementation. Inspired by constitutional AI, LLF comprises two steps: feedback modeling and self-improving, as shown in Figure 4. The former employs SFT to train the feedback model, enabling it to provide language feedback based on X and Y. The latter allows the model to refine its responses based on the language feedback C. Feedback modeling. The training process utilizes a dataset. D is a set of triplets X sub I, Y sub I, C sub I, for I ranging from 1 to n, where n is the size of dataset X sub I, denotes the prompt, Y sub I represents the response, and C sub I is the corresponding language feedback. Let the probability of C sub I given X sub I and Y sub I parameterized by theta denote the probability of the target sequence C sub I given the input sequence X sub I, Y sub I, and the model parameters phi. The training objective of the feedback model can be expressed by the cross-entropy loss. L sub phi is equal to the negative expected value over samples X sub I, Y sub I, C sub I drawn from the dataset D of the logarithm of the probability P sub phi of C sub I given X sub I and Y sub I. Self-improving. We first collect the initial model's response Y to the given prompt X online. Then we gather feedback C is equal to M sub phi of X and Y from the feedback model M sub phi. Finally, we have the initial model generate responses. Y star is equal to M sub theta of X and C, conditioned on this feedback. For example, Y may suffer from redundancy and hallucination, while C will remind the generation of Y star to avoid these problems. Based on online sampling, it often enables Y star and Y to exhibit significant differences in certain aspects. For example, reducing redundancy, thereby generating more learnable preference pairs. Experiment. We empirically verify that LLF offers several key advantages over traditional binary feedback. Unified preference. As language feedback typically optimizes responses along key dimensions, models can easily learn genuine human preference beyond pairs. Rich information. Since the feedback model can generate a substantial amount of language feedback, LLF can effectively serve as a robust synthesizer of preference data. Specifically, we train Chameleon 7 billion parameter for T2I and TI2TI, Lava 7 billion parameter and Lava 13 billion parameter for TI2T, Quinn2 Audio 7 billion parameter for TA2T, and Quinn2 VL 7 billion parameter for TV2T based on eval-anything 200K. For more details about the training setting, please refer to the appendix, Training Details. Improvement with unified preference. As shown in Table 2, LLF synthesized preference pairs reflect more unified human preference, enhancing all modality alignment performance. We observed that DPO and RLHF using binary pairs falls short in some modalities. However, with LLF, they yield positive improvement across all modalities. Interestingly, we find that the improvement of LLF on Lava 13 billion parameter is greater than that on Lava 7 billion parameter. This suggests that LLF performs better on stronger models. Efficiency with rich information. LLF provides richer information and supports efficient preference data synthesis. As shown in Figure 5, despite having only a smaller amount of language feedback, DPO plus LLF outperforms DPO with binary feedback. At the same time, the reduction in data amount does not significantly weaken the capabilities of LLF. This suggests that in all modality alignment, labeling many binary preference pairs is less effective than labeling a smaller amount of language feedback. Ablation study. Feedback model is necessary. As shown in Table 3, the feedback model generates language feedback on the initial model's responses to hold out evaluation prompts, which are then used to regenerate these responses. Results indicate that this approach yields improvement while replacing the feedback model with the initial model does not achieve comparable positive effects. Evaluation. Eval-anything. Currently, evaluating all modality models relies on human experts for assessments, which is inefficient and costly. While combining benchmarks for individual modalities could offer a broader evaluation, differences in data preparation, post-processing, and metrics across benchmarks hinder accurate performance assessment. Additionally, all modality models uniquely select the appropriate modalities based on user queries, enabling seamless cross-modal synergy, a capability that traditional single-modality evaluation pipelines fail to capture fully. To address this gap, we deliver our evaluation framework specifically designed for all modality models, eval-anything, including all-modality understanding, AMU, for assess models to simultaneously process and integrate information from all modalities, and all-modality generation, AMG, evaluate a model's ability to follow user instruction, autonomously select modalities, and work synergistically across different modalities for output. Composition of evaluation dataset. All-modality understanding. All modality models aim to both understand individual modalities and combine information across them to generate high-quality responses. To assess their comprehensive multimodal processing, we create 164 test entries, each containing textual, visual, image or video, and auditory, audio or speech components. These interconnected modalities require the model to integrate all inputs accurately, as failure in any one modality leads to incorrect answers. For instance, as shown in Figure 6, if a model fails to process visual inputs, it may miss that the person in the picture is frightened. Similarly, without auditory processing, it might not understand that the person's fear is due to a barking dog. We use GPT-4 to evaluate model responses on a scale of 1 to 10. However, previous studies underscore limitations in multimodal evaluation that rely on a single human annotation as a reference. As the number of modalities increases, so does the complexity, making it harder to reach consensus and increasing subjective bias in single annotations. Moreover, since GPT-4 lacks true multimodal comprehension, evaluating only its text responses doesn't confirm if essential information from each modality is fully understood. To address this, we gather responses from 10 annotators and extract key terms from each modality. As illustrated in Figure 7, the distribution of multiple annotations mitigates the bias associated with single referenced evaluation. Additionally, the inclusion of key terms enables GPT-4 to more accurately detect potential errors in its responses. The details for AMU can be found in Appendix Evaluation. All-modality generation. In generation tasks, all modality models can outperform single modal ones by delivering diverse information across multiple formats under the same user query. To achieve this, they must follow SSI principles. Select relevant modalities automatically to reduce redundancy. synergistic integration for maximum information gain, and instruction following in each modality, SSI. The overall score for the AMG task is as follows. S sub AMG is equal to X sub T V and A raised to the power of 1 multiplied by alpha sub T V times the sum of S sub T and S sub V times S sub T V. Instruction following. To assess instruction following, we design 100 prompts per modality. Using GPT-4o, we score the text and image outputs. For audio and video modalities, inspired by TIFA pipeline, we create multiple choice questions based on the prompts and employ Quinn 2 audio and Quinn 2 VL as evaluation models. This process yields independent modality scores S sub T, S sub V, and S sub A, each ranging from 0 to 10. Modality selection. Properly combining modalities in the model's response can provide rich perspectives while reducing redundant information. We employ 25 crowdsourced annotators to identify the expected modality combinations for given text instructions. The voting process results in one of the quantitative metrics for AMG task, with appropriate rewards and penalties applied based on the modalities generated by the model. As shown in Figure 6, alpha represents the percentage of human votes for each modality combination. And if the model outputs all three modalities, this parameter will be 1/3 of alpha sub T, V, and A. Modality synergy refers to the consistency between different modalities in a model's responses. We assess modality synergy by training a judge model with human annotations obtained through a data synthesis. Specifically, we develop a data synthesis pipeline centered on LLM-based agents that utilize tools to invoke audio, image, and video generation models, constructing a dataset with textual inputs and multimodal outputs. We employ human annotators to annotate preference data considering the synergy between different modalities in each response, and then train a judge model that allows all modality input. As shown in Figure 6, responses with high synergy scores, S sub TV, S sub TA, S sub VA, should show high relevance and consistency between modalities, with visual and auditory elements enriching the text from various perspectives. More details on training the judge model can be found in Appendix Evaluation. Evaluation results and analysis. Human and AI agreement. In the modality synergy task, after training on the 5K preference dataset, the experiment reveals a 66.4% agreement rate between the judging model and human annotators. These figures are consistent with human agreement ratios reported in similar studies on modeling human preferences in the multimodal large language models domain. Most models in Table 4 support partial modality input and have baseline scores, but Gemini 1.5 Pro outperforms others due to its ability to process all three modalities. In the AMG task, the average scores is relatively low, with no model demonstrating a clear advantage across all subitems. The results indicate that, compared to modality generation, models are more advanced in modality understanding, consistent with the development trends of all modality models. Truly all modality model. Current models still fall far behind all modality models. For all modality understanding, models using only a single modality score less than half the maximum points, as shown in Table 4. Even Gemini 1.5 Pro, which processes both visual and auditory input, fails to attain a perfect score. Unlike humans, who integrate information from multiple modalities, these models are limited by their inability to perceive different modalities in a fully integrated way, even though they perform nearly at the human level within individual modalities. Moreover, models align poorly with human choices when selecting output modalities, as illustrated in Figure 8. Humans can adaptively choose the best combination of modalities based on the instruction. In contrast, models tend to output either only textual information, resulting in information loss, or all available modalities, causing redundancy. The limited multimodal capability, especially in models trained mainly on text, hampers their ability to synthesize information effectively, making it difficult to balance detail and conciseness. Conclusion. In this work, we make the first exploration of fine-tuning all modality models using human preference data across diverse modalities. To ensure alignment with human intentions, we have open-sourced the eval-anything dataset, incorporating 200,000 annotated human preference data across modalities. Our proposed alignment method leverages language feedback to capture complex modality-specific human preferences, significantly enhancing the model's ability to follow instructions. To assess the all-modality models, we developed an evaluation benchmark, eval-anything. All data, models, and code have been made openly available. Ethics impact. Our data collection, approved by the Institutional Review Board, will be released under the CC by NC 4.0 license. The dataset integrates QA data from open source and API-based models, offering the potential for developing AI aligned with human intentions. However, while it could theoretically be misused for harmful purposes, we are committed to promoting safe AI technology. Limitations in future work. Despite having 45 experienced annotators, the team lacks sufficient diversity, which may limit the representativeness of human preferences. To address this, we plan to recruit a more varied group via platforms like Amazon MTurk. Additionally, the absence of all modality foundational models and open source restricts validation to individual modalities. So we encourage community efforts to develop such models and aim to expand experiments across more models. This is an ongoing effort with the goal of scaling the dataset to millions. My summary. This paper proposes a framework for aligning all modality models, capable of handling text, image, audio, and video inputs and outputs, with human preferences. The authors introduce a large-scale dataset, eval-anything 200K, covering diverse subtasks and annotated with both binary preferences and detailed language feedback. They introduce a new training approach that leverages these rich language annotations to improve alignment significantly more than binary feedback alone. And they also have an evaluation suite, eval-anything, designed to test all modality understanding and generation, which includes how well models select and combine multiple output modalities. The goal is to ensure that any-to-any, text to image, audio, video models more faithfully follow human instructions across varied tasks.